Hi everybody, I'm Margarita Castro and I'm very excited to share with you today our work on a combinatorial cut and lifting procedure with an application to 0-1 chance constraints. And this is a joint work with my supervisors Andres Siré and Chris Pate from University of Toronto. So in this work, we focus on binary optimization problems. So here we have a linear objective and we have a feasibility set that can be defined either by linear or nonlinear inequalities. And the only thing that we require from this set is that we have a binary decision diagram encoding for it. So in this talk, first I'm going to explain what are binary decision diagrams and how we can encode the solution set of a problem. And then I'm going to explain how we actually use them for combinatorial lifting and also a cutting plane procedure. And I'm going to end with some results for normally distributed linear chance constraints. So binary decision diagrams, they're basically layer-directed acyclic graphs that represents all the feasible solutions for a set X. So I'm going to explain them with this little knapsack example, where here we have a PDD for it. And the main idea here is that for each of the variables of the problem, we have a variable associated with each of the layers of the graph. And the arcs are going to represent the possible values that the variables can take. So for instance, here it would be x1 equal to 0, and here x1 equal to 1. So the idea here is that if we take any path from the root node to the terminal node, it will give us a complete variable assignment, So for instance, here we have x1 equal to 0, x1 equal to 1, x2 equal to 0, and so on. So we say that we have an exact BDD for a specific set X if there's a one-to-one relationship between all the paths here and the solutions for this problem. So in this case, we actually have an exact BDD for this knapsack constraint. So now I'm going to explain how we actually use this graphical structure for our combinatorial lifting and cutting plane procedure. So for the combinatorial lifting, we mainly focus on 0-1 disjunctions to compute values that we call D-slags or disjunctive slags. And we use these values to rotate or tilt our inequality so we can increase its phase dimension. So here I have a small example. We have 3 points for X. The convex hull is the triangle. We have a valid inequality here and a disjunctive slag that is negative. So we use this quantity to now rotate the inequality and get a new one. And here, in this case, we actually have a facet defining one. So the main idea of these D-slags is that they measure the change of the maximum left-hand side value for inequality, whether we fix the variable to be equal to 0 or to be equal to 1. So it's basically the difference between solving these two optimization problems. And the nice thing that they have is that if we choose any of these D-slags that are different to 0, the lift inequality is quite easy to compute. It's just small perturbations to the left-hand side and also to the right-hand side of the inequality. So this procedure is actually closely related to several other lifting procedures in the literature, especially we find one in the disjunctive programming literature that have a lot of nice connections with ours. So in terms of theoretical guarantees, well, we first showed that actually the lift inequality is valid for our problem, that in fact we have that the new induced phase has higher dimension than the previous one, and also that the lift inequality is stronger than the original one. So we don't have to save all of them, we just have to save the lifted one. And also some additional properties that we have is that we identify certain conditions for if we apply this procedure iteratively, we actually can converge to facet defining inequalities. And also we show that, and here's where the decision diagrams come into play, is that we can compute very efficiently in polynomial time these D-slags using the decision diagram. We can compute actually all of them at the same time. And also we show basically that even if we don't have the exact decision diagram, we can use relaxed ones, and our procedure is still valid. Which in fact, these relaxed decision diagrams are just basically a discrete relaxation of our original set. So now that I showed this very general procedure, I'm going to show how we can actually obtain a first inequality to lift using also decision diagrams. And the main idea here is to represent all the solutions of the BDD using a network flow polytope. So here we have original variables x, we have the y variables that are the flow variables passing through the diagram. And this is the important part that is different to other cutting plane procedure based on decision diagrams, is that we relate the flow variables with the original ones using what we call these joint capacity constraints. So for a given value of x, we can see these constraints as giving constraining how much flow can pass through a set of arcs in the graph. So what we do now is that our CGLP is basically the max flow version of the polytope that we had before. So we remove these constraints here where we impose the flow to be equal to 1. And now we're going to maximize the flow over the graph. And the nice thing that we prove is that we can identify if a point is inside the convex hull of our set X or not by solving this CGLP. And if it gives us a value equal to 0, we know that it's inside, and it's different, we know that it's not. So basically, this is what we use to create our what we call general PDD flow cuts that have this specific shape. And here, these coefficients come from the dual solution of our max flow problem. And we show actually that all the inequalities of this type define the convex hull of X. So the only issue with the approach that I just showed is that it can be challenging to solve depending on how big this BDD is. It could be a huge LP problem. So we propose a relaxation. That is our combinatorial BDD flow cuts. So the idea is that we replace these joint capacity constraints with individual capacity constraints for each of the arcs. So the polytope looks like we see here. And the nice thing is that then when we go to the optimization version to create our CGLP, it's just a max flow problem over the decision diagram. So we don't have to create the LP based on the decision diagram. We just have to compute the max flow using any combinatorial procedure that you want. And for the cuts, well, we use the classic max flow min cut duality. So the main idea, and here I show with a little example, we have the same decision diagram that we had before, an infeasible point, and now the values of this infeasible point are going to represent the capacities over the decision diagram. So we compute the max flow here. We see that is less than 1, and actually is 0.4 given by these two arcs here. So this is our min cut. We use our min cut to create our combinatorial cut. And actually, in this case, the combinatorial cut that we get is a cover cut. So we can actually recover some of the classic cuts that we have in the literature. And the only bad thing about this approach is that since it's a relaxation of the original polytope, it might not be able to cut all the fractional points. So basically, I'm giving you two alternatives. The general one, that can be more computationally expensive, or the weaker one that can be faster in practice. So now in terms of our, where we tested this procedure, it was in 0-1 chance constraints, where the coefficients are going to be Gaussian. So we have, as I said before, a linear objective. We have M chance constraints. The coefficients are Gaussian, so we can reformulate each of these constraints as second order cones. And in our application, what we did is that we have one BDD per each of the constraints using the second order cone reformulation. And we actually build, instead of exact ones that could be very large, we build relaxed BDD. So we limit the number of nodes that we have in each of the layers of the graph to have a more computationally efficient procedure. So in terms of experiments, we apply everything, implemented everything over Cplex. We tested their second order cones over. We have the general cuts with the lifting, the weak combinatorial ones with and without the lifting. We tested over 270 chance constraints instances with cuts at the root node and 1 hour time limit. And we also desactivated a pre-solve and dynamic search for all procedures, which was also quite surprisingly good for Cplex. I don't know why, but that was the case. So in terms of results, here first I'm going to focus on the left-hand side of the graph. So we have the number of instances solved over time for Cplex and also for our two approaches with and without the lifting. So we can see the Cplex is this dark blue line that is below. So it's solving less instances that or specific cuts, the general ones and the weak ones with and without the lifting. Actually, we're able to solve with the German cuts plus the lifting 31 more instances than simplex. And now in the right-hand side of the graph is the gap at time limit. So we have the accumulated graph for simplex and our other techniques. And we can see also that our techniques are above simplex, and we actually achieve with the best one a 42% average final gap reduction. So thank you very much for your time. I just wanted to finish with a quick summary. And if you have any questions, please don't hesitate to contact me or ask me in Slack later on if you prefer. And you can find also our paper available on arXiv. So thank you.